Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we talked about strain, and before that we talked about stress, and last we also discussed about Hooke's law and modulus of elasticity. We saw the definition of modulus of elasticity, and modulus of elasticity is actually of three types. That is called Young's modulus when it's longitudinal stress divided by longitudinal strain, then it is the ratio is called as Young's modulus. Similarly, if it is bulk stress divided by bulk strain, or we call that volumetric strain, the ratio is called bulk stress or bulk modulus. And third one is modulus of rigidity, so that is defined as shear stress divided by shear strain. We saw some application of all these concepts like basically till. Let's see some more cases, then we will continue with the next topic. So here we have one problem mentioned, and it's a little bit different. Here are three rods AB, BC and CD. Fortunately all are having same area of cross section, and a load of 10 kg is hanging in the system. Three rods connected in this manner, their length is mentioned and their Young's modulus is also given. And now it is asking about find the shift in point B, C, D. Means it's basically like, because this end is fixed, so what is the elongation in AB will be the shift of point B. Elongation in AB plus BC will be the shift of point C, and similarly elongation in this part and this part will be the point will be the shift in point D. So another point here that you need to keep in mind is that here one weight, one load is hanging through all three rods, is it? So what do you like what you will say about the tension or force, is it? If area of cross section is same, then we can also think about what is about stress in each of the rod. So in this situation, is it, because area of cross section is same, then I can say stress will be also same. Otherwise, if area of cross section is different, that example I can give you. Let's say it's another case. So here we have a system of even variable cross section like this. So area of cross section A1, area of cross section A2 and A3, and let's say this is being pulled by some constant force F, and this is the fixed end. So in this situation, if I talk about these three, this is, let's say, rod 1, 2 and 3. So in all these three rods, what will you say, what you will think about the tension or the force acting on each of the rod? So we here are like even if in this situation mass is also there, then also things will not change. But in this situation, if mass weight is there for rod, things will change, is it? But nothing is mentioned about weight, so we will consider rods are massless, okay, or either have negligible mass. Rods are massless or weightless, is it? So whenever like in series 3, 4, 2 rods are mentioned, so in that case you can always write the tension or force acting on each rod will be equal. And if area of cross section is same, then I can here write, even if area of cross section is same, then stress in each rod will be also same. So that means in part AB, BC and CD, stress will be also same. So now we have like given everything. Now let's calculate the elongation in part AB. Its length is given as 0.1 meters. So then, so we know already Young's modulus is equal to stress, that is force divided by area multiplied by delta L into L. So now rearranging it, I am getting the extension is given by FL divided by Y into A. So this is the general expression. Now I can write shift of point B is equal to extension in rod AB, is it? So shift of point B is equal to, you can write extension in rod AB, and that will be equal to what? So this I can write delta L AB is equal to force is equal to how much? Equal to 10 kg weight. So 10 into Z. Length is given as 0.1 meter divided by Y. Young's modulus is 2.5 multiplied by 10 to the power 10, and area of cross section is 10 to the power minus 7. So that's all, simple, straightforward. Let's simplify it. This is gone, and 10 to the power here it's left with 10 to the power how much? 3, because 7 it's gone. So 10 by, then it's 100 by, so it's coming out to be 4 into 10 to the power minus 3 meter, or that you can write 4 mm. So this is the shift, or this is the also extension in part AB. Similarly, you can write shift of point B, that is equal to 4 mm. Now like shift of point C, so that will be equal to delta LAB plus delta LBC. We already got this 4 mm. Let's calculate this one also. So that is 4 mm plus delta LBC can be written as F, that is, this is equal to F multiplied by LBC divided by YBC into area, because area of cross section is same. Just substituting the values, so it's 4 mm plus 10 into 10 into 0.2 length 2 divided by YBC, it's coming out to be 10 to the power 10 multiplied by area, that is equal to 10 to the power minus 7. So this is left with 10 to the power 3, and this multiplying it, we are getting it, it's 20, this is coming out to be 4 mm plus this is gone, so we are left with 20 multiplied by 10 to the power minus 3. So this is coming out to be actually 24 mm total extension, right? So shift of point BC, that is equal to length, extension in length AB, extension in rod BC. So we are getting extension in BC is 20 mm, this is 4 mm, total it's 24 mm. And exactly in same manner I can calculate for CD part, or shift of point D. So shift of point D, that will be equal to delta LAB delta LBC plus delta LCD. We got already this. Let's calculate delta LCD. So that is equal to how much? Force 10 into 10 into 0.15 divided by Young's modulus, that is coming out to be, I did small error. Actually for Y BC part, Y is given as 4 into 10 to the power. Here I have taken only 10, so I need to multiply it by 4. Then it will be divided by 4. So it will be like 5. Just take care of it. So it's coming out to be 4 plus 5 mm, and that is equal to 9 mm. So just take care of that. Now here this, and divided by 10 to the power 10 Y multiplied by area 10 to the power minus 7. Simplifying it, this is all gone 15, and this is coming out to be 15 into 10 to the power minus 3, that is 15 mm. Then shift of point D is equal to delta L AB delta L BC delta L CD. Now we have everything. This is 4 plus 5 plus 15, that is coming out with 24 mm. So that's all your problem. The new thing you should keep in mind on that point you should learn from this concept is that in such case tension in the rod will be equal. Is it? In this situation also tension will be equal. If area of cross section is also given as equal, in that situation your stress will be also equal. Rest thing is basic application of the concept that we have just learned. So let's see more cases, more problems. Okay, next case is elongation of rod under its own weight. What it mean actually? I hope you're understanding already. Let me still tell you that this rod is having length L, mass M, and A is the area of cross section, and yes, Y is the Young's modulus. So now it's asking, like, because if I just consider this part, This will be also having some weight. So this weight will be applying some force on this upper end. So because of that, some stress will be there in this part, some extension will be there. So continuously if I talk about this point, then this, because upper end can't apply force on this part, right? You must be agreeing with that. The lower end will be like hanging with this junction, is it? So the lower part, weight of this lower part will be the force acting on this part and on this like junction basically. So the stress or tension at this point is the weight of this part. So you can see actually as you are going from here to the upper end, tension or stress at every point of this rod is changing, and because stress is there, so the rod will extend by some amount because of its own stress or stress due to its own weight. Now the question is, you are asked to find that stress, right? So first thing you should keep in mind here is that because the tension in this rod at every point is changing, it's not constant, and whenever there is continuous variation of something is there in problem, always you should have that the problem will be solved by integration. Yes, there are some methods you can go directly like but basic approach is only integration. So let me first tell you the approach, how we exactly solve this case, then I will tell you the direct method, then you can apply that one also, but understanding the approach is also important. So let me first that how we will actually apply, how we will solve this problem. So this is the, now in this situation at every point stress is varying, is it? So stress in rod at every point is changing, right, or variable. So in this situation what we do is that I will consider a very small element. Let's say this is a small element which is at a distance of x from the lower end. You can take that distance from upper end also. Accordingly your expression will change and little bit calculation. Final result will be still same. So let me take this rod of length dx. This is small element. Here to show you I have drawn it still quite large compared to the rod, but in practical situation this dx is very small element. So you can write dx, it's like very small element. So I can take the tension or stress in dx element is almost constant. Tension or stress in dx element can be assumed to be constant. Okay, then I got dx is what? Length of my small element. What will be the tension in this? So see, total mass m divided by L is the length. This is what? Mass per unit length, we call it lambda, or its linear density of rod. Then you must be understanding that at this point the force or the tension will arise because of the weight of this x length rod, is it? So let me write this point P. At point P, tension will be equal to weight of x length rod, and that is equal to what? How much? So T I can write at x distance from the lower end is equal to weight, that is equal to lambda mass per unit length multiplied by length, then this is the mass, multiplied by g, that is the weight, and that is equal to tension. So we are getting it m divided by capital L into x multiplied by g, right? So we got tension, and because this small element is like very small, so I can take almost in this small element, the tension is constant. So I got tension divided by its area of cross section, then I will get stress. So stress sigma x is equal to tension divided by area of cross section, that comes out to be mxg divided by L into A. So this is stress. Now because of this stress, this dx length will expand by some amount. So let the expansion in length of dx part is d delta. D delta is even smaller. Then what I can write, strain is equal to d delta divided by dx. This is the strain. Stress I already got, Young's modulus already there. Let me just so y is equal to, this is stress divided by strain is d delta into dx. Now we are asked to find total expansion or total extension. So this implies d delta is equal to sigma x into dx divided by Young's modulus. Let me substitute the values. So here we will get, substituting these values, this is m x g divided by l a into y into dx, right? So finally we are getting, this is the expression for extension. So d delta, let me write, integrate it now, mg by l a y taken constant out dx, integration what, 0 to total length, 0 to total change in length, and integration is simple. So we are getting delta L is equal to mg divided by L a y. Integration of x dx will be x square by 2. Substituting the values, we are getting mg L square divided by 2 L a y. Simplifying it, we are getting mg L divided by 2 a y. So delta L I am getting straightforward, it's mgl divided by 2ay, right? So this is the method of integration we are getting. This is the final result. I was talking about that you can get this result straightforward also without even going for integration, but that has a limitation. Limitation is that only when the stress is varying linearly, is it, then only you can apply that result which I am going to tell you. If variation is like little bit different, then still you will have to go exactly with the integration method. Okay, so what is that? So direct how you can go is that we know already, if I was hanging here weight how much, w, then what will be the extension in this? So then you know already delta L is equal to f L divided by a into y, is it, where f is the load, right? So how much here, if w load is hanging, then you must be writing it w, is it, force is w, L by a into y is the change in length. But what is happening here, it's changing continuously from 0 load here, f is equal to 0 to f is equal to mg. Do you understanding it? At this point, because there is no part, hanging parts, so there is no weight, so tension at this lower end will be 0. At this upper end, total weight of this is hanging with this end, so the tension at this point will be equal to weight of this rod. So it's continuously changing from here to there. So what happen actually, I can take, it's changing from 0 to mg, so on an average I can take the average weight of this is actually half of it, is it? So or otherwise you can take it's half of the weight, average weight is like hanging here, is it, that is equal to mg at half of its length. That way also you can, but otherwise you can simply take it's like average value is half, so that half will come from there. So next thing is like it's mg, half is the weight multiplied by length divided by a into y, and this is directly you can write. But it has a limitation is that if things are varying linearly, then only you can apply it this way. If things are a little bit different, then always you have to go with the integration method. So this is how we can calculate like whenever something comes like continuous variation, you can go for it, you can apply this method and you can get the result, is it? So let's see more problems. Okay, see one more case. A rod of mass capital M, length capital L, a weight, this is a weight of W is attached to its lower end. Find total elongation in the rod, Y is the Young's modulus of the rod, and A is the area of cross section. So it's sort of like mixed problem what we have seen earlier cases. Here rod is also having some weight and additional weight load is also attached to it. You can simplify this problem in like 2-3 ways. One way is is it? So let me first, so you can treat this system is equal to like one rod plus elongation due to this weight plus another is elongation due to its own weight, is it? So this is elongation due to this, elongation due to its own weight will be equal to this complete system. This you know already, so let's say delta, I can write delta L1, that will be equal to WL divided by Y into A, force upon area, and simple straightforward. Due to its own weight we know already mgl by 2ay. So then we are getting this, you can write this is delta L2. So total delta L elongation is coming out with this plus that WL divided by YA plus MGL by 2AY, and that will be the answer, right? Another way is you can consider again a small element. So total tension at this point will be equal to what? Tension due to this weight plus lambda into x into g, tension due to this much weight. Then this is the tension divided by area, area will be the stress, and then again you will write d delta is equal to what? This. So this is equal to sigma x divided by area, this is basically divided by y into dx. Substituting this is w plus lambda xg divided by total area multiplied by dx, integrating 0 to L, and check, we will get still same result. So this is w by, and y will be also there, this y. So w a y integration dx plus this is lambda g upon ay into x dx, integration 0 to L. Now see it, integration dx will be simply L. So this is what? WL upon ay plus lambda, if I am substituting then it's mg by LAY, and this is x square by 2, so 0 to L, substituting the limit, so it's L square by 2, 1 L gets cancelled, and simplifying we are getting WL by AY plus MGL by 2AY, and still we are getting same result. So if you are, again you can see here the variation of stress load is linear. So this type of problem you can treat it in this manner also. So I hope you should be in position to answer this type of cases, to solve such problems. Let's see new cases, more cases. Okay, see the next topic is Poisson's ratio. It's Poissons, Poisson's ratio. Sometimes we call it for like just to make it easy, Poisson ratio is also sometimes it is termed as. So what it is actually, let's see, let me explain it. So let's consider here one rod is hanging like this, and if force is applied, so initially it has, let's say R is the radius of cross section of rod, Young's modulus is y, which because Young's modulus does not depends on the material, so it will not change, but we don't even require it here. And let's say its length is L, and R is the radius of cross section of rod, L is its length. So initially let's say no force is applied. Now what will happen when a force is applied on this rod? It will expand. So finally the situation will be, this is the rod will start expanding, and definitely when it is expanding its length will increase. So length was earlier this L, and then final length will be, let's say, L prime. Length has increased, and in this way the radius which was earlier, this radius will also change, let's say R prime. Is it? So once some force is applied on this rod, so radius or diameter, so if I say D is the diameter, then D prime is the final diameter of rod. So now in this situation, what is strain? strain we define its change in configuration. So change in configuration, two things are changing here simultaneously. Its length is changing, so there will be strain there also. And another thing, its area of cross section is changing, or I will say its diameter and its radius is also changing. So yes, both changes are happening. So we will see that here actually there are two strain. Is it? What is that? So we call this strain when change in length, it's along the length, so we call one is called longitudinal strain, that you already know, and it's I can write change in length divided by original length, and that will be equal to what? L prime minus L divided by L, and this I can write delta L by L. This is called epsilon longitudinal, or let me write it simply, epsilon L. So this is longitudinal strain. Another one is simultaneously its radius and diameter is also changing. So there will be one change in configuration in that lateral dimension also. So for that we define a more like one more term, that is called lateral strain. So you can write this is equal to the ratio of change in lateral dimension of rod divided by original dimension. So that can be written as, what is that? Radius is also changing or diameter is also changing. Both are changing simultaneously, and the ratio will be like whether you are calculating it from radius or diameter, it doesn't matter because ratio will still remain constant, is it? So now in this situation I will define one more, that is epsilon lateral, and this is equal to delta R divided by R, or that would be R prime minus R divided by R, or that also like delta D divided by D equal to D prime minus D divided by D. One more thing you can see it here is that R prime will be definitely smaller than R, similarly D prime will be smaller than that, you can see it here also. So definitely this quantity will be negative. So to make it positive I need to put one negative sign here. So it's minus, minus, minus. So lateral strain is coming out to be minus. Let me now express it only in terms of radius. So this is lateral strain. Then what is Poisson's ratio? Poisson's ratio is simply, it is the ratio of lateral strain to longitudinal strain that is termed as Poisson's ratio. Simple. It's denoted by sigma. I know sigma we have used it for stress, but still you should keep it in your mind. Poisson's ratio is also denoted by sigma. So, but it will be mentioned, yeah, like in problem if it is given, it will not be like simply sigma is given and you are not mentioned, nothing is given about it, whether it's stress or Poisson's ratio. That confusion will not be there, so no need to worry about that. So this will be equal to simply what? Epsilon lateral divided by epsilon longitudinal. This ratio dimensionless, unitless. So sigma is also, or Poisson's ratio is also dimensionless and unitless quantity. And this is equal to what? Minus delta R by R divided by delta L by L, and rearranging it you can write minus delta R by R multiplied by L divided by delta L. So this is termed as Poisson's ratio. It's just small terms. Sometime like this is given and change in length and original length, then you will be asked to find that change in radius or contraction in radius and diameter, so on. There you will be required. So straightforward things will be there. Just keep the formula in your mind, then you will be understanding it exactly what. So whatever it's asked, you should be able to answer this. So this is just like small term that is called Poisson's ratio. Okay, next is bars under varying load. Basically, this is a one experimental setup where like one specimen is used, and here this is a setup I have drawn it simplified diagram. Actually, computers are connected here to measure the stress, force applied, and extension in the rod. Everything is computerized here, and when like this is being expanded, this is specimen. It's a force applied and area process everything. So stress versus strain graph is plotted, right? From the Excel sheet, whatever we are getting the data. When we plot the graph for some like aluminum and copper material, then the graph looks like something this. And this graph tells us a lot about this material. And we need to understand those points. So here initially, when we are applying, let's say stress, here the stress increases, strain increases. And this ratio become like almost constant, and this a proportional limit is there. I'm like proportionally it increases. This A point is called proportional limit. So what happened up to this point, sigma is directly proportional to like strain, or stress is directly proportional to strain. If we go even beyond this, and what happened actually up to here also, if you are removing the stress, it will simply particle will show the elastic behavior. It will be like deforming forces are removed. It will again come back to its original shape and size. So elastic properties are still there up to here. A. As you stretch it further, means as you increase the stress further, it reaches up to B. And B is called actually elastic limit. I was talking many times. Elastic limit. Actually, what is B? B is that point, means up to which the elastic behavior of material is sustained. Means up to B point, if you are removing the deforming force, the material still has tendency, capability to regain their original shape, their original dimension. So the elastic property of material are still sustained up to point B, and this is termed as elastic limit. After point B, if we increase the stress further, what happened, you can see it here, the stress increase is very less, but strain increase is high. So the material start flowing like a fluid actually, and this behavior is termed as yielding of material, and the point C is called as yield point. Yield point. If you increase the stress further from here, strain also increases, but in this situation you can see the increase in stress is less, strain is more. So overall from point B, the stress required, is it increasing, is less, strain is more, and up to here it's showing elastic behavior. So this is called elastic region, and beyond this it's like flowing, it's more expansion is taking place. And what will happen if we are removing, let's suppose if the stress is removed here, in that situation will it simply stay there? No. Will it regain the original shape and size? No. What will happen? It will try to regain the original shape and size, but not completely. So it will come back, but not completely. Some small deformation will be set in the material, and this small deformation we call set. So set is what? It's the permanent deformation that has been settled in the material, in the specimen. This is termed as set. And after point C, if we are increasing further stress, strain also increases, and there exists one point T. I mean like this is the maximum stress the material can bear, and this D is termed as ultimate stress. So this is the maximum stress a specimen material can bear. If you go further, even when we are not increasing the stress, force is applied still. Remember here some stress is there, means force is applied, but that cannot be more than this D, ultimate stress. If you just apply it further, like force is applied, it will expand more, and finally it will break down. So E is called breaking point or fracture point, or breaking point. Now what happened actually, this is one of the like graph I have shown. If you just consider, do this experiment set up with the different types of material, is it, let's say with the plastic, is it with the rubber band, with the aluminum, steel or glass, then this graph is not exactly this way. It has different, like sometime it will go from here and up to here, it simply break. So this will be the behavior for more brittle materials. They will not have any like this area under this graph will be very less. They can't expand more, they just expand a little bit and then finally break down there. So that like way, if the area under this graph is like less, we can say it's like more brittle if it is breaking down here easily. So that's why like this graph tells us a lot about, and I hope like these are different points what they mean. I already explained. Breaking point, fracture point, where finally is breaking down, is it? Ultimate stress, it is the maximum stress the material can bear. Yield point, after point B, even small increase in stress resulting in more strain, that means material start flowing, expanding like a fluid. So that reason, that behavior is termed as yielding, and this point C is termed as yield point. B is the maximum stress up to which the elastic behavior of material is still sustained, means up to point B, even if we are removing the deforming force, the material has abilities to regain their original shape and size. So that is termed as your elastic limit. A is the point up to which sigma is directly proportional to epsilon. So these are different points, and this is the result of this experiment. Let me write just like these little point little bit. Okay, so just a little bit description about different points. A, already I explained. Proportional limit up to this point, stress is directly proportional to strain. Slope of sigma versus epsilon graph up to this point give you Young's modulus. Elastic limit up to this point, stress material or means up to this point or stress material has tendency or capability to regain its original configuration or removal of deforming force. So that means you can say the elastic behavior of material is still sustained up to this point. C is called yield point. After point B, small increase in stress result in large increase in strain. That means material flow like a fluid, and this behavior is termed as yielding of material, and the point C is called as yield point. Set. So now if the deforming force is removed after B, means elastic limit, then material try to regain its original configuration but does not regain completely. Some permanent deformation is settled in the material, and that is termed as set. Point D is the maximum stress the material can bear, that is termed as ultimate stress, and E is the fracture point at which finally material break down. If you further stress it, it finally break down. So this is all about this bars under varying load. This is one of the experiment. This graph we got when sigma versus epsilon is plotted, and that is all information we get about material. Okay, rod as a spring. So it's about behavior in case of elasticity. We know the behavior of spring. So let's say this is one spring constant K, its length, let's say L0. What happened when some force F is applied? There is some expansion in this spring. Let's say X is the expansion in spring, right? And what we write, F is equal to K into X, right? And K is spring constant. Actually, within the elastic limit, behavior of rod can be just replaced or can be understood just like a spring. How? Let me tell you. So let's say this is one rod which has A area cross section, L length, Y Young's modulus, everything is given. Now what will happen when some force F is applied on one of its like lower end? This will also expand by a small amount L, expansion in rod on applying force F. So then what I will write here, I know actually delta L is given by F into L divided by Y into A, and here this can be written as F is equal to YA by L multiplied by delta L. Is it? F force can be written as, so now if you compare these two expressions, is it? One, and 2. Then it's exactly like X is what? Expansion. Here that expansion is delta L. Force is force applied F. So this YA by L is what? It's equivalent to spring constant. So YA by L, it's called K equivalent, or spring equivalent is spring constant of rod. It's equivalent spring constant of rod. So in this manner we can consider, or we can treat a rod just like spring, with spring constant is given by YA by L. Y, Young's modulus, is the area of cross section, L is the length of the rod. So now in SHM chapter you must have studied the series parallel combination of spring, is it? So in like series, if two springs are connected, this is K1 K2, then what is K equivalent? K equivalent is given by K1 K2 divided by K1 plus K2. Exactly in same manner, so if here two rods are connected having length L1 A1 Y1 L2 A2 Y2, then what is its K1? K1 is equal to, equivalent K1 is equal to A1 Y1 divided by L1. K2 is equal to what? Y2 A2 divided by L2. So in this situation, this rod can be also replaced by some like K equivalent, and that is equal to K1 K2 divided by K1 plus K2. Exactly in same manner. Similarly in parallel combination, so like we know actually in parallel combination these are two springs, is it? Spring constant K1 K2. So then K equivalent is given by what? K1 plus K2. Exactly in same case, so if we are having two rods connected in series, in parallel, then in this situation again like just see it. So two rods, length L1, area of cross section like Y1, area of cross section A1. Similarly L2, Y2, A2. So spring constant K1 will be equal to what? K1 is equal to Y1 A1 by L1. K2 is equal to Y2 A2 by L2. Then in this situation also K equivalent is given by K1 plus K2, just like spring. So this is the behavior of rod as a spring. So whenever like this type of problem is asked, like whatever problem can be asked, let me just give you one example, it will be more clear to you. Okay, see one simple example. Say mass M is attached with the rods as shown in figure. Two rods connected in this manner, and one mass is attached to the lower end in this manner. So M mass. This mass is slightly stretched and released. Whether motion of mass will be SHM, and if yes, find its time period. So we have just seen actually these two rods will be equivalent to what? These two rods will be one spring, another spring, and this mass. Now you tell me whether its motion will be SHM. The answer is yes. So now next come is what is the time period. So now for that we can easily get it by just simply calculating K equivalent. So what is K1? So let's see. So motion will be SHM. Motion will be SHM. Right? Correct. Now K1 is equal to what? Y1 A1 by L1. K2 is Y2 A2 by L2. Because springs are in series, so what is K equivalent? It's K1 K2 by K1 plus K2. This is K equivalent. Then what is the time period? So time period is given by, for this system, time period is 2 pi under root K equivalent by M. Right, that is the simply time period, and we know everything K equivalent and M. Just a small correction, it's M by K equivalent, not, so it's M by K equivalent. Now we can substitute everything, like, so time period is coming out to be 2 pi under root M, and what is K equivalent? K equivalent is, this is K1 plus K2 divided by K1 K2, and the values of K1 K2 already given here. So this is the answer. So that's how you can see, by treating rods like spring, we can very easily answer this type of problems, even when like little bit complex situations are given, 2-3 springs connected in series parallel exactly in same manner, just like 2-3 rods connected in series parallel. Treat them just like rod, simplify, get the K equivalent, and further solve it, whatever it is asking, time period, frequency, and everything. Like so, similarly, because now you can see rod is acting like a spring, so means when we are stretching the spring, some elastic potential energy is getting stored in the spring. So if rod is acting like a spring, then if rod is stretched, some energy will be stored in the rod also. Let's get the expression. Let's calculate that how much energy will be stored in the rod if it is also stretched. Okay, so elastic potential energy stored in rod. So let's consider this is the rod, Y is the Young's modulus, A is the area of cross section, L is the length. Now this lower end is being pulled by some force F. What will happen? It will expand. So let's say delta L is the expansion in the rod. Let me write. On pulling by this force F. So now what is the energy stored in this rod? That is the question, right? So first thing is like we can answer very easily by treating it just like spring, is it? So let me first get the expression for delta L. So delta L is equal to what? Stress upon Y into L, and that can be written as okay, let me write the expression in terms of only stress. So this is the, because stress, this delta L by L will be strain, so Y is equal to stress by strain, and this is what we are getting, expansion in the rod, delta L. What is K equivalent? K equivalent is equal to YA by L, this is K. So if this is a spring, K equivalent is K, YA by L, expansion is delta X is equal to delta L, then what is the energy stored in this spring? So elastic potential energy, stored in spring, U can be written as what? Half K equivalent into delta L square. Simple, by treating it just like a spring, right? Nothing complex, remember that. Easy, straightforward. Let me substitute the values. Y A by L is what? K. What is delta L? Sigma L by Y. So let me simplify it. Or yeah, that is right. Okay, or otherwise I can even substitute things in terms of strain also. So okay, let's solve. So this is the energy stored. Let me simplify it further. So what we are getting, energy U is equal to 1 by 2 into YA by L multiplied by, this is equal to sigma square into L square upon Y square. 1 by gets cancelled, 1 L gets cancelled, so we are getting 1 by 2. This is sigma, this is A into sigma square into A into L upon Y. Clear? And we know already sigma upon epsilon is equal to Y. So I can write basically sigma upon Y is equal to what? Epsilon. Right? So now here see, this can be written 1 by 2 sigma multiplied by sigma divided by Y into A into L. And what is this? So total energy is equal to 1 by 2 into sigma into epsilon. This can be expressed as epsilon multiplied by A into L. And what is this? Volume of rod. So this is the total energy stored, and we can write energy density, that will be equal to what? U divided by volume, and this is equal to 1 by 2 sigma into epsilon. So we are getting energy stored 1 by 2 sigma into epsilon into volume. Energy density is energy stored per unit volume, that is equal to half of sigma into epsilon, and this is all about. So I think like you should not have any problem, because here we are simply treating this rod just like a spring, and you know very well what is the energy stored in the spring, and you must be remembering the formula, what is the K equivalent of the spring, or like what is the K equivalent for the rod, that is YA by L. Delta L expression, you know, then energy stored simply half K x square K delta L square. Substitute the things, rearrange it, and whatever the expression, you can just simplify it, then this is the answer. This is also expression depending on what is asked to you in the problem, so accordingly you can use that relation. 1 by 2 sigma into epsilon is the energy density of elastic potential energy stored in the rod. So this is all about basically like topics that we study in elasticity. Okay, see one simple application here. So one problem is given. So steel wire of length. So length of the wire is given as 2 meter. Area of cross section is given as 1.2 10⁻⁻7 meter square. Cross section is stretched by a force. So force applied is 36 Newton. Calculate stress, strain, increase in length, and work done in stretching the wire. And Young's modulus is given as 1.8 into 10⁻11 Newton per meter square. So it's basically everything data is provided. It's a straightforward problem. So first stress. Stress is equal to what? Force divided by area of cross section. Force divided by area of cross section 36 divided by area of cross section is 1.2 into 10⁻⁻7. That comes out to be this, and Bharati 3 into 10⁸ Newton per meter square. So this is the stress, and Young's modulus is also given. So strain is equal to what? You can write stress divided by y, Young's modulus. So 3 into 10⁸ divided by it's 1.8 into 10⁻11. So this comes out to be 30. Then it's like 310 divided by 6 or into 10⁻⁻3, or that is equal to 5 by 3 into 10⁻⁻3. This strain, this is the strain. Next it's asking increase in length. So delta L is equal to L into strain. That comes out to be 2 multiplied by 5 by 3 into 10⁻⁻3 meter. This is the delta L, change in length. Work done is in stretching. So work done in stretching, work done, it basically asking the energy stored, because work done is equal to elastic potential energy stored. Elastic potential energy stored in wire. So that we know already. This is equal to 1 by 2 sigma into epsilon into volume. That is equal to area into length. So everything is also given to us. So it's 1 by 2 sigma is equal to how much? Let's substitute 3 into 10⁸. Epsilon, it's mentioned as 5 by 3 into 10⁻⁻3. Area of cross section is given as 1.2 into 10⁻⁻7. Length of the, it's 2 meter, right? Simple, straightforward. Just you need to remember the formula, substitute. So this is the energy stored, and that is also equal to work done. Let me simplify it. 2 3 gets cancelled, power -3 -7, so it's coming out to be -10. So it's basically we are left 5 into 12, so it's like 6 into 2, this then it's gone, so it's 12 and it's 6 into 10⁻⁻2 joule. So energy stored is, you can write 0.06 joule. This is the answer. This is the elastic potential energy stored, or that is also work done in stretching. Work done in stretching equal to 0.06 joule. Let me just check the calculation. This 3 gets cancelled. 5 into 2, it's this, and 2, then it's 6, and power -10, 2, then it's power, yes, it should be. So this is the answer to the problem, and this is all about basically elasticity. Let's continue with the viscosity topic in the next class. Thank you so much.